Raymond. Okay, so this last talk is going to be quite work that we are doing quite recently. So this is about curvature in non-commutative geometry. So I should say this is joint work with Hausdorff. Okay, so we have been working on this for quite maybe 4 or 5 years now. I think so, and he will give a talk next week in the conference with more details. I'll give the conceptual or maybe a little bit general picture of the things. So, okay, so so the background really, I mean, from differential geometry, we know that if you have a Riemannian manifold, right, we can attach to this different tensors. For example, Riemann curvature tensor Rijkl, support tensor, or you can attach Ricci curvature Rij, or you can attach Ricci scalar or a scalar curvature, just the scalar function on your manifold R. So these things exist, right? We can define these things. So the standard way to do these things these days, I mean, the modern approach is that from G you go and construct the unique compatible torsion-free connection, the Levi-Civita connection, and then there are formulas that gives you the curvature of any connection, and you apply those purely algebraic formulas to this Levi-Civita connection, and you get these different this tensor, and then you contract it with metric in a special way. You get this one. You contract with metric again. You get that one. Okay, so now the backbone of kind of non-commutative Riemannian manifolds are spectral triples, right? So, so I want to think of a spectral triple as the basic ingredient in a non-commutative Riemannian manifold, right? So AHD. So if you take this concept seriously, then it's a very, very natural question, of course, to ask what's going to happen to curvature, right? So what's going to happen to other metric invariants of this object? So then the question is, what is Rijkl in this case, etc. So this is a still, I think, is an open question, and maybe we will never find an answer, full generality, or maybe this is not even important, or maybe there's no way out, or something like that. But so far, I think there is very, very good understanding what this should be. This scalar curvature should be. So on a conceptual level, we very well understand that. And above that, we can also calculate it in some cases, in the case of non-commutative tori. So that can be calculated. And I'm going to present results of calculations to you. So that's kind of plan. So, okay. I'm not sure I should define a spectral triples for this group. Should I define it or I shouldn't? Should I? Okay, so I got a consenting voice, so I'm glad you said yes. So because I was going to define it, but I was shy about defining it. So very good, thanks. Thanks for not being shy. So there is pi. Okay, so there's this guy. So first of all, what is A? A is a star algebra. It's unital. And of course, it's over C. Now you represent it on a Hilbert space, H, which is the Hilbert space that appears there. You have this operator D from H to H. which secretly is your Dirac operator. So abstractly, you just first say it's a self-adjoint, in general, unbounded operator. And these data are connected. For example, the commutator of, you can say D and pi of A is a bounded operator. So these are bounded operators. And this D is not a crazy operator. It has a compact resolvent. For example, in particular, its spectrum is discrete, is going to infinity. So D has compact resolvent. So in the sense that form D squared, or say D, I would say plus minus I inverse belongs to compact operators. So this really tells you that the spectrum of D is discrete. It's like a spectrum of elliptic operators on compact manifolds. I'll mention that even a little more later. Okay, so I think that's basically what we have. And then if this thing is even a spectral triple, there is also a parity operator, a chirality operator, gamma from H to H. Gamma squared is 1, and D gamma is minus gamma D. So D is odd, and there is also this operator J, which is charge conjugation. But these are kind of, then you're really putting more structure. And of course, we have Cohn's reconstruction theorem, Alan Cohn's reconstruction theorem, that tells you that if you have this data plus commutativity plus regularity plus some technical conditions, there are some axioms to be satisfied for non-commutative manifolds. Then he showed that actually, in fact, they come from a spin Riemannian manifold. So this is why we think spectral triples are backbones of non-commutative Riemannian manifolds. Okay, so to do then non-commutative Riemannian geometry, you really want to look at some basic invariants. For example, volume of this guy, AHD, what should be our distance function. And then, as I said, eventually, the kind of ultimate signature of geometry is curvature, of course, right? So we want to look at curvature eventually. So to get off the ground, let me just mention that there is an obvious invariant here. That's the kind of metric dimension, or spectral dimension of this guy. So this is the spectral dimension, or metric dimension. For this guy, it basically is the condition that absolute value of D to the power minus D belongs to this ideal of operators I denote by L1 infinity H. This is the domain of Dix-Smith race, but what does it really mean? It just means this. Sigma lambda I from 1 to n, is essentially O of log n as n goes to infinity. You shouldn't worry about the inverse of D, because D has finite kernel. You throw away the kernel, and then the issue is independent of throwing away that finite dimensional kernel. So that's D1, exactly. So lambda I now belong to, I conveniently belong to spectrum of absolute value of D to the power minus D. Yeah, exactly. Right. Now, why this is reasonable? So this is already the main result, the first main result of spectral geometry is used here to justify this. So this is, let me just recall, Wiles' law. So Wiles' law for compact manifolds, compact Riemannian manifolds, tells you that anytime you have elliptic differential operator like this, for example, in the original case, it was for Laplacians, but it really works for Dirac, for similar operators. Boyle's law tells you that, in fact, in a situation like this, we can always read volume can be heard. I mean, you can read it from knowing the spectrum of the operator. So you can just say volume can be heard. So what does it mean? It means that if you take a spectrum of this, now I'm going to change notation. So if mu lambda I, so let me put it mu I, is equal to a spectrum of this guy D, or rather absolute value of D, then, so maybe I put mu n, then the rate that they go to infinity is controlled by volume, essentially. So this is mu n goes to infinity as some constant CD, and then there is volume of m to the power 1 over d, and there is n to the power 1 over d as n goes to infinity. So there is an asymptotic formula like that. So in particular, mu n minus 1 is growing like an inverse, where in front there is volume of m, and there is some other constant which I put maybe alpha n, but I just absorb it in this asymptotic sign. As n goes to infinity, sorry, yes, n minus d, exactly. Yes. So, oh, sorry. Oh, this is this one. Yes, thank you. Yes. Yeah. So then, what does it mean? It means that if you sum mu n minus these guys, you are really like summing 1 over n from 1 to n. And this is, of course, log divergences. So this is O of log n. So there is a log divergence. So you have this log divergence, and okay, so it's not trace class. However, it's in the domain of Dirichlet trace, and in particular, it tells you that volume of m up to some constant, let me call it alpha d, is related to, it can be read from Dirichlet trace of absolute value of d to the power minus d. So this is the kind of first formula that we can get from this kind of Boyle's law in the classical case. And you can take this formula and bring it to the non-commutative world, because non-commutative world is a spectral world. So all the spectral notions make sense, right? So now what we can do is we can take this number, if this condition is satisfied, as the volume. And in fact, you can define a volume measure or volume measure on AHT. You can define this functional phi of A to be Dirichlet trace of A, absolute value of d to the power minus t. Right? So not only we can just compute integral of 1 dg over m. In fact, we can compute integral of f dg over m, right, for any f. So this is just volume, but this is really the measure. And similarly here, we can also compute the volume measure by this formula. Which d? This one. Yes. So the definition is this. If it exists, it is the number such that absolute value of d to the power minus t belongs to this ideal. So this ideal consists of all operators whose spectrum grows like this. there is only a unique one if it exists. Well, yeah, this is the smallest one. Yeah, after that there's 0. Yes, sure. Yes, right. Is that clear? Good. Okay. So now, okay. So we can read volume from this kind of picture. That's good. But volume is just the first step. That's not enough. To go ahead, we introduce spectral zeta functions. So this cannot contain too much information. The real information is in the spectral zeta functions. So this you can define zeta, for example, delta S to be trace, operator trace of Laplacian to the power minus S, or even you can define a kind of more kind of refined version of it, of zeta functionals to be trace of a Laplacian to the power minus S. So these guys, they are defined. Well, what is Laplacian? First of all, Laplacian is d squared, is Dirac Laplacian. Or if you work with generalized Dirac operators, this could be the usual Laplacian of functions or on forms as well. You just take d equal to d plus d star in that case. That's okay. So by this condition, if you have a spectral dimension d, then we know that this guy is, for real part of S, bigger than d over 2 is an analytic function. So on the right half plane, somewhere, this is an analytic function, right? Now, okay, so the picture is like this. You have this S equal to d over 2, and you have constructed your zeta function, a spectral zeta function from there. But what is not obvious is that this has an analytic continuation to the whole plane with poles at certain points, and we have complete information about the residues in terms of the operator itself. So, for example, we know that one can, I'll indicate the proof because I need it, that in fact residue of this guy, zeta delta S, at S equal to d over 2. I mean, from that estimate that I have over there, it's quite clear that this guy, this zeta function, has a pole at S equal to d over 2, because the series is going to be like 1 over n, and that's divergent. So because there we are taking the usual trace, right? That's the operator trace. That's sigma 1 over lambda I to the power S. Right? Okay, so there is a pole here, but what is not obvious that this residue is related again up to some constant to volume of n. So the residue at top pole is related to volume of n. And in fact, the residue of this guy at S equal to d over 2 minus 1, there is a subleading pole that's related to total scalar curvature. D G over M. So this is total scalar curvature. Okay. Okay, now, so we see that total scalar curvature is if you believe in this statement, you can hear total scalar curvature of a manifold too, right? So that's the spectral invariant. So in particular is a spectral invariant. So it just means that you really have a chance to formulate these concepts for spectral triples if you're careful enough. But then computing the invariance is a different matter. So this is kind of circle of ideas that goes into definition of curvature invariant, the scalar curvature, and then for computing it, you need pseudo-differential calculus, and there's no way around that. Okay, so let me just recall. So what's the technique that you use here? So this guy is sigma 1 over lambda I to the power S lambda I different from 0. Right? So this you cannot do anything with it if you just know this. But what really gets you off the ground is Melling's transform, 1 over gamma s, integral 0 to infinity, e to the minus t lambda, t to the power s over t dt. So this guy is, this equation is true for real part of s given 0. So what you need to know at this stage about gamma function is that this gamma s is different from 0 at all places, and it has simple poles at 0 and negative integers. That's all you need to know. And of course, you need to know it. You need to know its definition as well to get this formula. This formula is more or less is equivalent to the definition of gamma, if you want. It's the same. You just turned around the definition. Simple poles at 0, minus 1, minus 2, minus 3, and we know its residues and everything. You know. So this gamma is really king of the moment, and actually king of the whole subject, really, secretly. Without gamma, we cannot do anything. So summing all those things over the spectrum, then you get zeta delta s, sum of 1 over lambda I to the s, lambda I different from 0, then you get 1 over gamma of s, integral 0 to infinity. Okay, sum of exponential of minus t lambda I. Fine. Lambda I different from 0, and then t to the s over t dt. Now you can write this even a little better. 1 over gamma s, 0 to infinity, trace of this operator, let me call it exponential of minus t Laplacian. And then there is a projection into 0 modes. We have to subtract them because I have subtracted 0 modes here, right? So we have to subtract 0 modes. So this p is projection into 0 modes, and the rest is what it is. Okay, so now you have an understanding of this guy if you have an understanding of trace of exponential of minus t. An exponential of minus t Laplacian is the heat kernel. So the technology then is to know as much as you can about heat kernel. So heat kernel is, or heat operator, if you want. So let me just say heat operator for the moment. Exponential of minus t Laplacian. Now, this is a smoothing operator, as we've been discussing in these courses. So this is a smoothing operator. It really sends L2 of your, for example, spinors into C infinity ones, right? So it means that its Schwarz kernel is absolutely a smooth function. So this guy has a smooth kernel. So let me write its kernel ktxy. So this is going from R positive, strictly positive for positive time, cross M to R. This is C infinity. Right. Now, okay, so the kernel of this operator now can be computed. So there is a theorem. So this theorem started, I think the first step was really by Meenakshi Sundaram and Pleyel in 1940s. And then the full kind of version that I needed was done by Gilkey and then Zilidovit. And I think maybe I have to add other names, but basically let me just like that. So the theorem is that on the diagonal there is a formula for this guy, k of t x x, asymptotically on the diagonal is given by 4 pi t to the power minus n over d over 2 a0 of x plus a1 of x t plus a2 of x t2, so on and so forth. as t goes to 0. So now, this is an asymptotic expansion only. Okay, so this is an asymptotic expansion. So in particular, the right-hand side may be divergent for all x and t. But that doesn't matter. You cut it somewhere, and then you get the information that you want. So that's asymptotic expansion. Now, these guys, A0, A1, and A2, all these coefficients, or for example, if we are working with Laplacians on scalars and functions, then these guys are smooth functions on the manifold, right? And these guys are polynomials in metric tensor and their covariant derivatives. So they are expressible as universal polynomials in G and its covariant derivatives. Okay, so these polynomials, I believe they are only computed in general up to order 6 or 8. 8. Up to 10 even? Okay, so maybe not very workable formulas. So these formulas, yeah, okay, so the thing is, the algorithms, they say works, but who can compute those algorithms? Who can run the programs because it becomes extremely complicated and cumbersome and heavy calculation after 10 and 12. But there are formulas up to A6 in Gilkey's papers, and then up to A8 has been worked out, and maybe A10 also. So, but let me give you the first 2, 3 that we need. So the first one, A0 of x is equal to 1. That's easy. The next one, A1 of x, is 1/6 of a scalar curvature. That's also not bad. And the next one, A2 of x, is something like, for Laplacian, Hausdorff Laplacian, I'm talking about 1/360. There is 2 Ri JKL, Ri JKL, minus 2 Rij, or Ji, plus 5, I think, R squared. Something like that. So there are expressions in terms of Riemann curvature tensor. And then there are others. Now, this one already implies Wiles' law. Thanks to this kind of relationship, already implies Wiles' law. This one tells us that we can actually get a formula for a scalar curvature in terms of either heat kernel or zeta function. By the way, now that we have come this far, let me give you the argument for why this implies. Yes? Oh, is that right? With this one, I see. Okay. Yeah. Okay. So this is the only notation I can understand. Yeah. Okay. So now, good. So now this one is okay. Now, why this is good? Why this implies something about analytic continuation of zeta functions and its residues and poles and all these things? Well, the trick is, the trick that was used actually by Riemann and everybody else in number theory, spectral geometry, using it ever after. The trick is this. Use this, okay, and break this integral into 2 pieces. So you just write zeta delta of S, that's Riemann's trick. You have 1 over gamma of S. Then you break the integral into two pieces. You go from 0 to epsilon, and then epsilon to infinity. Right? But this part, there's no problem at all with this part. Because at that point, in that region, I don't know, this is maybe infrared or ultraviolet. This is infrared region or something. I'm not sure. Anyhow, so in that region, this guy is exponential decay. And you're already subtracting 0 mode. So this is fastly going to, exponentially decaying to 0 faster than, of course, exponential decay is faster than any polynomial power. So this guy is holomorphic everywhere. It's just holomorphic, and 1 over gamma is also holomorphic. So this is holomorphic. Okay, for short time asymptotics, when you are near 0, then you can use this formula. We can use this formula. For small time, you can use this formula. And you plug in, and then you just compute the integral term by term. The integral is because replace it by that guy. You basically, all you need is just integration of t to the power m. That's all, from 0 to epsilon. Then you can read everything. So the upshot is that, indeed, the residue of this guy zeta delta s at s equal to d over 2 is this integral of a0 of x dg over m. But a0, if you know a0 is equal to 1, then it's going to be volume of m. And residues at all subleading poles, then you can also read the place of subleading poles. So let me open another window here. So the subleading poles, they are at top pole minus j, where j goes from 0, 1, 2. I mean, all the poles are located at that. But then at the subleading pole, you have residue of, that's the next term that's related to this one, comes from this contribution of this. It's very easy to see it using properties of gamma function and that. So residue of this guy, at s equal to d over 2 minus 1 is integral of a1 of x dg over m. But that's really total scalar curvature because we know that, or 1/6 of total scalar, we know that. So this is total scalar curvature up to some constant, universal constant. Total scalar curvature. Okay, so this is then this shows a way to go into a spectral to do these things in the non-commutative case. So in the non-commutative case, then let me just write down the formulas that you get. So there is some nuance in the formulas. Let me just write down the formula, and then that would be our working principle. You mean? Oh, that I don't know. Oh, is that right? One cannot, or can? Can, because it's integrable, you're saying. I see, okay. I didn't know that. Yeah. Oh, that's very interesting. Yeah, okay, so, yeah, I mean, I see, yeah, okay, so. So then you can read from that kind of formulas that in dimension d equal to 2, this curvature R satisfies the equation So what is the equation? The equation is that, okay, so integral of f r dg over m is equal to basically value of the zeta function equal to 0 plus dimension of kernel of, oh, made a mess here, plus trace of AP, F or FP. So remember, I introduced this before, zeta A delta S is trace of A, this kind of mollified or smeared, or not a smeared, kind of, I don't know what to, it's a functional, zeta functionals, right? So this is maybe F, because in this case we are dealing with this, right? So now, one of the things that I did not mention, I should have mentioned about that, is that these guys are always regular at s equal to 0. So there's no pole at s equal to 0. So I should have mentioned here that always regular at s equal to 0. So in particular, you can take their values. The value of these guys at s equal to 0 makes sense. And this satisfies this kind of equation for all f in C infinite of m. So then it just makes sense for spectral triples to define, sorry, it's f, yes. I'm switching between commutative and non-commutative. I'm kind of, yeah, at this stage, a schizophrenic person. For spectral triples, I can define R as, if it exists, unique solution of an equation like this, tau of A R, for you have a measure on your trace on your space, equal to zeta A delta S at s equal to 0 plus trace of AP for all A in A. So this would be your kind of equation that you want to solve. If you can find such an R, then you have found the scalar curvature. But this R belongs to, it's not a number, right? It is a density, it belongs to A, belongs to your algebra. Now, what about dimensions bigger than, spectral dimensions or metric dimensions bigger than 2? That the formula differs for D bigger than or equal to 2. It's really subleading pole, because D equal to 2, I mean, there is no subleading thing. Already you go, because D over 2 is 1, and you pass to 0, 0 is regular, so no residue. But for D bigger than 2, the equation that you want to have is that actually residue of this guy, A delta to the power minus S at S equal to D over 2 minus 1, it should be equal to tau of A R for all A. Okay. So this would be the equation in dimension bigger than equal to 3, right? Okay, so as I said, you can write definition of curvatures in terms of spectral zeta functions, or in terms of coefficients of the heat equation. You can go back and forth between the two by using Mellin transform and inverse Mellin transform. Okay, so now the case that we looked at was the case that actually was started by Alan Kahn. So this is there is a work of Kahn and Tretkov. So that's already around 1990. I think it was maybe 1989, 88. It started that time, and there's a preprint in Max Planck archives. Actually, you can look at the preprint. So they looked at non-commutative torus. But the novelty there is that for the first time, the non-commutative torus was not a flat object. They conformally changed the metric on the non-commutative torus. So let me look at non-commutative torus a theta infinity. Then conformally change the metric, flat metric. So what does that mean? It means that, of course, this trace that I'm talking about here, tau of A, is just a standard trace, right? So this is the usual trace that on the non-commutative torus. But now you define a new state, phi of A, to be tau of A e to the minus h. But this h now is a smooth element in the non-commutative torus. So h belongs to so it could be very general thing. It's an infinite series, infinite short series, right? So once you do that, it means that you're really now looking at these measures that are not kind of like Haar measures or homogeneous, because this guy is Haar measure, essentially. It's analog of Haar measure. If theta equal to 0, it's translation invariant and all that. But this guy is not, because this h is very general. So what is the operator they looked at? The operator is something that is just Dolbeault. You just start with flat Dolbeault. I mean Dolbeault operator. Dolbeault, Dirac, whatever. So what is it? You just look at this operator del bar, which is delta 1 plus I delta 2, right? Now, this operator goes from, you can imagine, goes from a theta infinity to a theta infinity, right? And then you look at its adjoint, del bar star, delta 1 minus I, delta 2, same. And then you introduce an even Hilbert space. So you just take H to be equal to a theta infinity. Direct sum a theta infinity. Okay, GNS completed. Okay, so if you want to work flat, then that's a spectral triple you already get, right? So you get a spectral triple by this method. So D equal to 0, say del bar star, 0. Is a spectral, defines a spectral triple. Right? So we define a spectral triple like that. But what they did is that they brought this into the picture. So for one copy that you have here, if you look at del bar, I mean, this del bar operator, you go from now a theta infinity to a theta infinity. Now, you take GNS construction of this guy not with respect to this metric anymore, but with respect to this perturbed one, right? With respect to this metric, right? So this GNS with phi. So you get Hilbert space. You get a different Hilbert space. It means that you're changing metrics on the fibers conformally. And then you take adjoint of del bar with respect to that metric. So then del bar star, so let me call it like this, is adjoint with respect to this new Hilbert space. Okay, so then your Laplacian, or maybe I should say H actually instead of this, but phi and H are the same thing. Then your Laplacian is going to be del phi star bar del bar. Okay, so that's the perturbed Laplacian now. That you have taken into account the conformal perturbation of the metric. So this is the perturbed Laplacian. By the way, if you do this construction in the commutative case, you really do get conformally perturbed Laplacian. It's the same construction that you do in that case. And now you are looking for solutions to this equation, right? So for example, what Gauss-Bonnet theorem is, and they were really looking for Gauss-Bonnet theorem first. So e.g. Gauss-Bonnet is saying this because we know that for the thing should be equal to 0, basically Gauss-Bonnet should say that this guy should always be equal to, put A equal to 1. Basically, we have to prove that zeta 1 Laplacian at 0, right? That's the thing. Plus this thing is dimension 1 should be equal to 0 for all h belonging to a theta infinity. So this would be a reformulation of Gauss-Bonnet in spectral terms for the non-commutative 2 torus with respect to that metric. And they were trying to prove this, and they took really, really huge steps short of proving this. They simplified the expressions. You get there are huge expressions using this Kahn's allowance to the differential calculus, but then they just could not prove this. Eventually, they proved it in, I think, when was that? 2009, was it? Around that time. And then what we did, how we entered into the picture, was from this kind of uniformization theorem. Let me tell you a little bit about uniformization. Also, this is done by Kahn and Tretkov. So this was, I think they papered in 2009, I believe. So what uniformization tells us? Well, uniformization theorem for the torus, it tells us the following thing, right? We know that metrics up to conformal equivalence, right? In general, for surfaces, metrics up to conformal equivalence is the same thing as complex structures, right? So the same thing as complex structures. So if you are looking at metrics up to conformal equivalence, means that you are looking at complex structures. Now, what is the moduli of complex structures on tori, on the elliptic curves? These are things in the upper half plane, right? So this is basically upper half plane. So there is a parameter. I'm sorry, I have to use tau for this parameter, which is always, everybody uses tau here belonging to H, upper half plane, imaginary part of tau positive, right? So modulo action of SL to Z, right? So every point that you take here gives you a complex structure on the torus and gives you an elliptic curve. But then to introduce the metric information, you want to conformally perturb a metric that represents this complex structure, right? So what they did was the case tau equal to I, basically. This I is exactly this I that I have over there. This is the conformal parameter. So the question that we started is, well, so obviously, even in the commutative case, this is not the most general metric, right? Because you just have taken this conformal class of just one conformal class, and you perturb the metric in that conformal class. What if you take all other conformal classes, right? What if you take general tau and you do the same, you ask the same kind of question, is such a thing true? Turns out to be true. The equation you get for this at the end was at 2 terms. The equation we got had 4 terms, and then, okay, so there was a lot of computer calculations and a lot of things. I will show you some formulas soon. But the thing that got us started was really this kind of proof of Gauss-Bonnet theorem. So then, so how you do this then for general tau? For general tau, you do this. You introduce this factor tau here. Instead of I, you put a tau, and here becomes tau bar. And then your analysis becomes a little more complicated, but you have to do the analysis. But then it is true that in general, this is true. So one can say that if you believe in this sort of wisdom of uniformization in the non-commutative world, which we don't know what it is, by the way, then that you can say that the theorem is actually proved in full generality. But okay. But then, of course, this question, you're here really not asking the hardest question. The hardest question is, what is R itself? It's like a quantity that we don't know, but we are able to show that its trace is 0, right? But what is that quantity itself? We didn't know it exists, but then when you do the calculation, it comes out to be, and it's also existence proof. Yeah, I don't know any a priori arguments. That is it. I don't think. Okay, so then the real question, the real difficult question was to find this R that satisfies these things, and then we did the calculation. So now, if you give me kind of access to this, maybe I still have 5 minutes, or because we started late. We started late. Okay, so this I know I have to turn this on. And, okay, so yes. Yes, trace. Yes, yes. It's not a trace. No, no. That's a good question. This tau is not a trace. It's a KMS state, and there's a modular operator, and that kind of gives you the twisting of the trace. How far is it from the trace? And then this modular operator also comes into the formula for the curvature. So that's kind of quite interesting. Yeah. Okay, so yes. Okay, so hopefully I can work this now. It looks like. Oh, I have to put a screen mode. He said. Yes. Put on the screen mode. Is it? Oh, you already did it, maybe. Okay. Yes. Okay. So now. So this is the paper that I was talking about. Well, Paulo Tretkov was Paulo Cohen, so the same person. So they started in the late 80s with tau equal to I. There is a spectral zeta function, and that's what you want to. Okay, so which one is the laser pointer now? Do you know which one is the laser pointer? Oh yes, thank you. Okay. So this is a spectral zeta function, and this is the equation you want to prove. You want to simplify, show that it is equal to 0 or whatever. Okay, so the equation that they found in this old paper is this. With explicit formulas for these functions f and these modified truncated logs Lm like that. Okay, it was very hard to show that this is 0, and there was some even doubt that whether this is 0 or not. But so eventually, as I said, for tau equal to I, it was done by them, and for general tau by us. In fact, it turned out that this Gauss-Bonnet theorem for theta 2 is true. So that's now the final proof in our case. Instead of 2 terms, you had 4 terms. Now this functions k is explicitly computed. Is a very explicit function, sine hyperbolic functions like this, and then this nabla is log of the modular operator. So basically, commutator by h, log of the modular operator. So this is really commutator by h, essentially. This thing comes into the picture. So to compute this, okay. So this is the formula for k, and I don't mention that. Now, let's go to a scalar curvature for a theta. That's the formula that I had. So I don't have to recall that. So the formula for scalar curvature was obtained simultaneously by us and Kahn Moscovici. I think it was 2011. So this is the formula that you get. This is element R. You can say R is equal to this guy. So there are three functions, R1, R2, and W, explicitly functions. I will show you. And then these functions, okay, so you do functional calculus. You apply this kind of nabla operator, this log of the modular operator to this. This is the commutator. You get the operator that acts now on the elements of the non-commutative torus. And these are elements of the non-commutative torus. So this is some kind of Laplacian, you can imagine, acting on your conformal factor. And then there is this two-variable function acting on this expression, and this is the commutator. And there is this term IW acting on this commutator of this. And so in the formula, you can say it's manageable. And now the beautiful thing about this formula is that as theta goes to 0, this really converges to the Gauss's formula for curvature on surfaces, for conformally flat metrics. Every metric on the surface is locally on any surface is locally conformally flat anyhow. Okay, so this is the function. R1 is the sine hyperbolic function, written in terms of sine hyperbolic functions. And this is R2. Now, so this R2 is a rather complicated function. It's really amazing that this is an analytic function. I mean, there's no reason for this to be analytic, but it is an analytic function. So this is incredible function. It's analytic, so you can do functional calculus easily with that. And W is also analytic function. Again, is a quotient of these three expressions divided by that. And you see, there is no way to guess these formulas by algebra or by deforming some structure or some Q analogs of this or that. There's completely no way to do this thing. It just comes from a spectral geometry and hard calculation, and it's just, yeah, pseudo-differential operators in the non-commutative case. Okay. So then we looked at the four-dimensional case. These papers, by the way, are on the archive. So the four-dimensional case, you do more or less same game. You conformally perturb the metric. So here I don't use tau, I use phi 0, but okay, same thing. Then this is the equation that you want to solve for R. This is a spectral zeta function modified by A or functional. The formula in this case that we obtained is given by this expression. There is a function k, and there is a function two-variable function h. This nabla again is commutator by log of this conformal factor h. So this is this commutator. And k is this function. The two-variable function is given by that, by this expression. Now here, this function is really, this is just an operator. After you do functional calculus, this is an operator acting on elements of non-commutative torus again. And this operator is acting on elements. So you can see that this is some kind of Dirichlet energy that appears here. And this is some kind of Laplacian that appears. So this is a Dirichlet energy and Laplacian over there. So just again, explicit formulas for all ingredients have been computed. This is k, and this is h, two-variable function on the diagonal h. Off diagonal or the opposite diagonal s minus s, and that's it. Okay, so I think I just stop here, maybe. Okay, thank you. Yes, Eric.
So you have 2 or 3 examples in where you can see the power of
Yeah.
Is there any hope, or do you have any idea of proving in maybe limited cases where that an R has to exist without actually having a formula?
Yeah.
All, you have non-commutative tori of arbitrary size, right? Is there any hope of saying at least there has to be an R, it may not be computed?
Yeah, for non-commutative tori, I would say yes, that this should not be difficult for non-commutative tori. And the reason is that we have a very good pseudo-differential calculus, thanks to work of Alain. We have this. Very early on, he introduced the pseudo-differential calculus for non-commutative torus. So we have that. For non-commutative tori, we can do that. I think it should be possible. But finding a formula for R is different, because this is now is not just writing a formula. You have to. You cannot ask a computer to do a calculation for any n. You have to give the value of n also to computer.
No,
So, but okay, I mean, exactly. That's right. Yeah, that's right. Yeah, no, that's a valid point. Exactly. I think in that case, can be. Then in general, it's vastly open. I mean, this area just being started, being explored. I mean, it's vastly open. I mean, one has to really look at all kinds of examples that you can find. I mean, quantum sphere. I mean, Podlesh sphere. What is the idea of curvature there? And if you perturb some Laplacians there. But the problem is that the spectral dimension of that guy is 0. And there are no formulas in a spectral geometry that tells you that if a spectral dimension of z is 0, what you can do. I mean, the non-perturbed heat kernel has been computed. It's extremely complicated. It's not like heat kernel of smooth manifolds. For quantum torus, I mean, heat kernel of non-commutative torus, it's like, I mean, it has the features of a smooth manifold. It follows the same pattern for pi t minus t, and there are no log terms, there are no strange terms. But for the quantum sphere, it's an extremely complicated expression. It looks like a heat equation, a heat kernel for fractals. Because heat kernel for fractals also has been computed, and they have similar features. They have log terms, they have oscillating log terms, and they have. But what can you do with that? That's a very interesting problem. That's very, very interesting problem. And quantum homogeneous spaces, same thing as UQ2, and all these things also same. You have similar problems. So it's vastly open. I think it's a very interesting area for people to jump into and then make a difference, hopefully. I think it's vastly open. Yes.
Those formulas, yeah, big G and big H is a power series.
Mm-hmm.
So what were those formulas again?
Oh, those formulas?
Yeah.
Oh, you mean in terms of explicit functions, or?
Yeah, I mean, you had an expansion to like 6 power or something.
Oh,
G.
yes. And then.
And so is that what is G?
Oh, okay. So G is okay. So eventually, out of G, you construct an operator that acts on non-commutative torus. And then you apply this operator to these expressions in conformal factor, and then there you get the curvature. So.
And you know this formula exactly, or is it
Yes. No. The formula was written exactly in terms of this sine and sine hyperbolic functions. That's quotients. These are basically rational functions in sine and sine hyperbolic functions.
But it's in 2 variables.
In 2 variables. You look at on the diagonal and the other diagonal also. That was kind of just to convince ourselves that this is kind of reasonable function. But yeah, I mean those functions appear, and these formulas have completely wiped out in the commutative case. You don't see them in the commutative case at all. There is nothing in the commutative case. In this case, you just get this. This formula was computed by Gauss actually. If you have e to the h dx squared plus dy squared, what is the curvature of this metric? E to the h dx squared dy squared. Gauss knew that this is some kind of Laplacian of h times e to the minus h or something like that. There was a formula. I mean, Gauss calculated that. But this formula converges to that as theta goes to 0. But you see, there are so many things. I think it's. I think this should be related to quantum gravity somehow. Yes, please. Yes.
The statement about this scalar curvature in the 4 dimension is that the trace of it is not topological, but it attains its maximum classification.
That's right. Yeah, you can also, because there is this Einstein-Hilbert action, you can compute the Einstein-Hilbert action in this case, which would be just trace of this guy. And its maximum is attained at h equal to 0, I guess, right? Or h constants, yeah. In that case, this is the. So yeah, you can solve this kind of Einstein-Hilbert action, but what is the kind of Einstein equation in this case? Einstein field equation in this case. Yes. Maybe yes, yes. Okay, so okay.
What's the formula that would factor the
There should be, I mean, of course, Euler characteristic, I think, is 2. Even K-theory calculation shows that. But we have no idea of what this curvature is, the scalar curvature is. And I mean, Euler characteristic, exactly. So that's one of the paradoxes about this quantum torus. I mean, it is 2, yeah, because its compact operators direct some C. As an algebra, we know what the algebra is. So its K0 is 2-dimensional and K1 is 0-dimensional. So it's a strange object in many ways. It's not like, okay, yeah, but maybe more interesting. Yes.
I'm just wondering, so you explained in the Prometheus case that
Yes.
the volume and the total curvature has these great residues.
Mm-hmm.
So what about the other residues for D2 minus J?
So yeah, I mean, exactly. They are related to these other terms in the heat kernel, right? Right. So the next one is related to this term A2, which was combination of 3 terms: the square norm of the Riemann tensor, and then the other one was square of Ricci, and then square of a scalar curvature with some weights. Yeah. What? Not as nice as that. No, this is the feature of these Zilidovit-Bilki coefficients, of course. But now the thing that's very interesting to think about is Gauss-Bonnet in 4 dimensions. So that's really interesting thing to think about, even for the 4 torus, because then you have no idea what because it's not a scalar curvature. That's not topological invariant in 4 dimensions. There is a formula in something like that, but it's a different combination. But you see, in that formula, we have only understanding of 1 term. The 2 other terms, we have no understanding, right? So the hope is if you calculate, maybe if you have good eyes, you can separate terms and somehow says that, okay, this corresponds to Ricci, this corresponds to that, and you just throw away a scalar curvature first. But you know what I mean. There's a real problem here. There's a real interesting problem. Very interesting problem to deal with Gauss-Bonnet in dimension 4. Definitely. Oh, yes, there was a question. Sorry? This works only in dimension 2 and 4 so far. It cannot even be that ambitious, yes. Well, of course, Gauss-Bonnet, I mean, is immense. But no, but the formulas exist for all dimensions. By the way, these formulas that I wrote for scalar curvature is only for integral dimensions. There are spectral triples that have non-integral dimensions. What can you do with them? They are kind of fractal types, so it goes into this kind of business of how to define curvature for fractals and these things. So that's very interesting problem, very, very interesting problem.
For all cases, the Euler curvature is
0, yeah.
all these A's are, it's really A0, A2, A4, I think they're all nice.
Yeah, I think in the three-dimensional case, I think Riemann is a little more complicated, but it's not as complicated as 4. Yeah, but it's not as simple as 2-dimensional. No. I think there is another tensor or something like cotton tensor or something. The 2 of them, cotton tensor. The 2 of them completely. There are 2 tensors. Yeah, I think there are 2. So we don't know what is cotton tensor.
Okay, we take Masoud for the series.
Thanks.